Hey everyone. In this lesson we're going to be discussing the layers of Earth, or just the layers of the planet. And these layers can apply to other planets and other objects in space as well, but we're going to be focusing on the structure of the Earth today. And then at some point when maybe in our science class, when we get to our astronomy unit, we'll focus a little bit on how these ideas and these things that we see when we look at the layers of our planet can be applied to other objects in the solar system or other objects out in the universe. So to begin, there are a few different layers that make up the Earth, and they're listed here from the outermost layer at the top to the innermost layer at the bottom. So basically, if you were to have a diagram of the planet that looks like this, so like you've got half the planet here, and then the other half goes down that way. Um, then these layers sort of correspond, the way I've ordered them here, they correspond to where you would find them going deeper and deeper into the Earth's surface. So you'd have the thin crust on the outer edge of the planet, and this is not drawn to scale, but basically you'd have the thin crust on the outer edge, then the mantle inside that, and then the core inside that. And these can be divided up into smaller and smaller subsections. As you can see over here on the left, we've got the uppermost mantle, the asthenosphere, the upper mantle, and the lower mantle. So we're going to talk about these different layers within each of the three sort of big layers. And then also down here we can see that there's an outer core and an inner core that make up the overall core of the planet. So there are these three big sections: the crust, the mantle, and the core. We're going to talk about um, how we know that these exist. I mean, the crust is obviously fairly straightforward. That's what we live on right now. But we have ways of sort of examining and studying the structure of the planet inside, which I'll talk about a little bit. It doesn't show up so much on the slides because it's not the kind of thing that I want to test you on. What we're really going to focus on is some of the different properties and characteristics of these three layers, um, and what we do, or what each of them does, and what we can do with that knowledge. What knowledge do we have? What knowledge are we looking for still? So here's just a little bit of a diagram showing some of the different layers of Earth. Um, Basically what they've done in this diagram is they've chopped off almost half the Earth, and they've just separated the different sections. So we can see out here, this would be the planet's crust. This is the outermost layer. I'm just going to use a C because writing with the laptop's pen isn't very easy, so I'm going to do as little writing of letters as possible. But so out here, this outermost layer right here is the crust of the planet. It's a really, really thin layer, as you can see if you look kind of right here. You can see it doesn't extend very deep into the planet. It's a really, really thin layer, uh, just like a shell, like an eggshell or like the skin of an apple kind of thing. It's a really thin outer layer, and basically everything that we've uh, ever done on the surface of Earth or even underground all happens within this tiny, tiny layer. Inside of that, we have the mantle, which is this big hot orange thing here. It's orange because it's hot, basically. Um, and then as you go deeper and deeper in the planet, this is the inner core. I'm going to use IC for, oh, sorry, this isn't the inner core, this is the outer core, and then the inner core over here. So hang on, let me fix that. That's right. Okay, let's fix that. This is the outer core here, right there, and this is the inner core over here. So there it is. Those are the four sort of main layers. Um, and the planet gets really, really hot the farther you go into the planet. So out on the crust, the temperatures are, pretty comfortable, pretty low temperatures, given that what you guys might be used to, the average temperature of the planet is something like 15 degrees Celsius, which is not very warm. I mean, it's warm enough that, the water on the surface isn't frozen, and, we're not terribly uncomfortable if it's 15 degrees. But as you go deeper and deeper into the planet, it gets hotter and hotter to the point where it's thousands of degrees in the core. And in the core, it's basically the temperature of the surface of the sun. So it does get really, really hot the deeper you go into the planet. And we're going to explore a little bit of what we know about the different layers of the planet, and we'll talk about some of the different characteristics of those layers and what we're still trying to learn more about. Something that surprised me when I first learned about this is that even though we've tried to dig our way down beyond the crust, we've never actually managed to. So we're going to talk a little bit about one dedicated attempt to dig that far down. So of course we're going to begin with the crust. So first and foremost, the crust is really, really thin, and it might not look that thin when you read here that it's about 30 kilometers thick on average, but on the scale of the planet, that's not very big. So the planet has a radius of 6,371 kilometers. 6,371 km, kilometers. That's the radius of the planet. So that's the distance from the center of the planet, right here, to the outer edge of the planet, right there. So that distance there is 6,371 kilometers. Now, if the crust is only 30 kilometers thick, that's pretty thin. That's not really that deep into the planet. It's something like 0.2% of the way down from the surface to the center. So there's a really, really long way to go. Even if you got to the bottom of the crust, getting to the center of the Earth is a really, really long journey. Even if you set aside, the heat that's associated with going deeper and deeper into the planet. But the point is, the crust is really thin. Now, obviously, the thickness of the crust can vary. So I'm going to draw a little picture here. So if you've got land where you'll have cities and houses, and you'll have a lake or an ocean, and then you've got more land, and somewhere there's a mountain on the other side, right? Okay, so like over here we've got houses and cities and people, and then we've got a body of water right here. So there's a body of water in there somewhere, and then we've got a mountain going up here. So obviously we can see that if the crust is the outermost surface and then the mantle starts just below that, the mantle starts, let's say right here, then we can see that the thickness of the crust here is not the same as the thickness of the crust here, and that's not the same as the thickness of the crust over here. So what we can see here is that the thickness of the crust does vary depending on the shape of the landscape above it. Now under oceans, so in this kind of area, the thickness of the crust could be as little as just 5 kilometers, which is really, really thin, especially when you compare it to this number over here. So if we were able to get down to the bottom of the ocean and start drilling downwards to try and get into the mantle, it might only be about 5 kilometers down to get there. Over here, where we see, flat land masses, around where you'd find most of the continents, but not the mountainous regions of the continents, then that's somewhere like 30, 35 kilometers thick. So I'm going to say 35 here. just because of the example that we're going to examine in a second. But yeah, so basically it's 35 kilometers thick over in this area. So if we wanted to try drilling down from here, it's still not a lot compared to the scale of the planet as a whole, this 637.1 over here, but 35 kilometers starting here and trying to dig down 35 kilometers is not an easy feat. So that's sort of one of the problems with trying to dig down to the mantle, is that it's a long way for us, even though it's not really a long way for the planet. For us, who deal with things on the scale of meters, 35 kilometers is 35,000 meters, and that's a really, really long way to dig down. And then with mountains and stuff, and in mountainous regions, in land that's been uplifted, so like when there's geologic activity, it doesn't necessarily have to be a mountainous region for the crust to just sort of be thicker in that area, for the land to just be higher, in which case the distance to the mantle would be something like this. If I extend that line over to the left there, if I extend this line over like this, then the thickness of the mantle, once again, it becomes a problem. The thickness of the crust here, sorry, becomes enough of a problem that we struggle to dig our way all the way down to the mantle. And then, of course, mountains themselves pose a problem in that even if the crust wasn't particularly thick, the mountain is now adding several kilometers of thickness to it. Now, obviously, it doesn't make like a 30-kilometer difference, because the tallest mountain in the world, if we're starting if we're ignoring mountains and landforms that are already submerged or partially submerged in the ocean. So basically, if we're looking at something like Mount Everest, it's less than 9 kilometers tall. So it's really not that big. It's not adding a 30-kilometer difference that, like, oh, you know, on average it's 30 kilometers, but under a mountain it's 60 kilometers, therefore the mountain is 30 kilometers tall. That's not how it works. It's just that the landform isn't, it's not like it's 35 kilometers everywhere that's flat. This 35 in this area is not like it's not constant. It changes over the course of the planet, and then just on average it's about 35. So in some places it'll be 30, some places it'll be 40, some places it'll be 20, some places it'll be 50, and then on top of some of those you'll have mountains, and it becomes, from 50 it becomes, you know, 56 or whatever. So mountains do have an effect, but it's not as pronounced as it kind of looks with the numbers given here. But basically the idea is that the thickness of the crust changes depending on where you are. So if you're floating on a boat in the ocean, sure, you're several kilometers maybe above the ocean floor, but then once you get to the ocean floor, it's only a few more kilometers down to the mantle. Now, on the subject of oceans, the crust is made up of two different types of crust, I guess you could say. It's made up of continental crust and oceanic crust. So basically, the entire surface of the planet is covered in this thin crust, but that crust is fragmented into different bits, and those different bits are made of different things. And so some of them are called oceanic crust, and the reason for it is that oceanic crust is denser than continental crust. What that means is that if I have a piece of continental crust, let me draw it in green down here. If I've got a piece of continental crust, like a little cube of continental crust, and I've got a little cube of oceanic crust, I'm going to draw it in blue because oceans. Note that it's not actually blue. I'm using blue to represent water, even though we're talking about a piece of land. So if I have continental crust and oceanic crust, and I put them on a scale to see which one is heavier, if they're the same size and the oceanic crust is denser, then the oceanic crust will actually also be heavier. So basically, if it's If it's denser, that means that if I took a piece of each type of crust, continental and oceanic, and I weighed them, the denser one will be heavier. So the oceanic crust is heavier. So if we've got these different pieces of the crust floating on basically a sea of lava underneath, a sea of magma underneath, I should say, which is the mantle, which we're going to get to in just a second, then the denser stuff, the heavier stuff, the oceanic crust, sinks down a little bit more than the continental crust. So what that ends up meaning is that we have a piece of crust that's down here, and then a piece of crust that's up here, and another piece of crust that's up here. So this one over here would be continental crust. This one that's over here would also be continental crust. And this one that sinks down a little bit because it's denser and heavier is oceanic crust. So now if there's a cloud or a storm and it rains, all the water is going to pool where the land surface is lowest. So all the water will flow into this, basically this big hole between the two pieces of continental crust, and so that's where the oceans tend to form, is within that space, because the oceanic crust is dipping that much farther below. Now we'll talk about new crust and the recycling of old crust and stuff more as we progress into talking about things like plate tectonics and stuff, which we'll discuss in our science class actually. But basically the idea is that new crust forms when magma, which is basically just lava that's underground, when it comes up from the mantle. So like from the mantle we'll have a whole bunch of lava that's beneath the mantle, and then it comes up to the surface, or to the ocean floor, or maybe all the way up to the surface as lava. And here we'll have, if this mountain is actually a volcano, then we'll have a big magma chamber here within the inside of the mountain, and then when there's an eruption, it'll all come out the top there as a volcanic eruption. But new crust is made a lot of times in the middle of the ocean, where the magma rises up and then it cools and becomes new rock right when it reaches the surface. So then some of the rock that we'll find at the ocean floor is a lot younger than the rocks around it, because it's been newly made just a little while ago by magma that's rising up from deep within the planet. And then old crust gets recycled in the planet, as you see down in this diagram at the bottom. This oceanic crust sits sort of beneath the continental crust. So this piece of the crust, the edges of it will dip downwards into the mantle. And as it dips down into the mantle is really hot, and those pieces of the crust will melt, and that's how the crust gets recycled. So new crust comes up from the mantle, and magma comes up from the mantle and then cools to form new crust, and then the edges of the oceanic plates dip back down into the mantle where they melt. We'll get into this a lot more when we're looking at geology and the way that we can tell things about how old rocks are, and things about the pieces of the crust moving and stuff. But yeah, this is just a bit of an intro to it. Sorry about all the pictures on this slide. Hopefully it's not too hard to sort of follow what's going on. But yeah, that's about it for the crust. But now we're going to talk about one specific scientific endeavor that was done regarding the structure of the Earth. So this is something that you may have heard of, you may have not. It's called the Kola Super Deep Borehole. It's written in Russian just below there, because this is a scientific experiment conducted by the Soviet Union, or the USSR, several decades ago. Basically, it's a really, really, really deep hole in northwest Russia, and this was basically the result of a digging project where scientists and engineers tried to dig a hole all the way through the Earth's crust and try and make it all the way down to the mantle. So they had a whole bunch of fancy technology. They had to invent a whole bunch of new technology to create this hole and to be able to dig so far down. They ultimately reached a depth of more than 12 kilometers. So that's basically, that's if you took Mount Everest and you flipped it upside down and tried to stick it down this hole, you'd still have like 3.5 kilometers of extra space on top of the space that's taken up by Everest. So it's a really, really deep hole. It's deeper than the bottom of the Marianas Trench, which is the deepest point in the ocean. Um, it got a really, really long way down, but the problem is that the crust in this part of Russia is 35 kilometers thick, approximately. So if you've only gotten about 12 kilometers of the way down, they only made it about a third of the way through the planet's crust. Um, and this was 0.2% of the way uh, down to the center of the core. This was a really, really long project, and actually I found this great video for you guys to watch. Now, obviously, in this video lesson, you can't click on the link that's down here, but when I post this lesson, as long as I don't forget, I will include this link in the description. But also, your first assignment has been posted, and this link is in there. So you need to watch this video before you do the assignment, because a lot of the questions on the assignment have to do with this Kola super deep borehole. I believe the next slide is a picture, and I want to talk about the picture and give you a little bit of a warning if you are doing any research on this. So let's see what that holds for us. Okay, yeah, so if you look up a picture of the Kola super deep borehole, this is the first result that a lot of people tend to see. This is clickbait. This is not what the borehole actually looks like. The way they've tried to draw it here is they're trying to show that it's like, we've got like a town and roads and buildings and stuff all down in this space, and then we've got this giant hole with this huge diameter going across and then presumably super deep into the ground there. It's not the size of like a city. The hole itself only has a diameter of about 9 inches, I think, or about 23 centimeters. But then within that hole, it goes all the way down, more than 12 kilometers. So it's basically, the hole is about as wide as like a pizza, and then it just goes down for like ridiculously far. It's a really small but really deep hole. I'm going to show you a picture of how it actually looks today. So here's what it actually looks like. It's just a tiny little thing with this cover that's been welded onto it. Just in the middle of this pile of just rubbish, just metal that's rusting and things that are falling apart. It's basically just an abandoned site now. And there's this little unassuming circular disc that's just welded shut in the middle of this wasteland. But underneath that cover, if you could take it off, is a 12-kilometer drop down to the bottom of the hole. So this project, the history of the project and stuff, is sort of covered in that video, which I'm going to have you guys watch for your assignment. Yeah, this was an interesting endeavor that that these scientists and engineers took to try and get to the mantle. They ultimately had to stop for a couple of different reasons. One, it was an expensive project. Two, they weren't expecting the temperatures to be quite as hot as they actually were once they got down to a depth of 12 kilometers. They were expecting the temperature to be more like 100 degrees Celsius, and they found that the temperature was more like 180 degrees Celsius. So it was 80 degrees hotter than they expected it to be. and that caused some problems for the actual uh, drilling purposes, because basically what happens is that when it gets that hot and the pressure is that great, when you're down 12 kilometers, there's a lot of pressure from the rest of the crust that's above you, that the rock at that depth stopped behaving like a solid rock. It started to behave more like a really, really thick fluid, or more like a plastic, and it was not really working with the drill that they had. It wasn't really easy to drill any farther than where they actually got with that technology. So they ran into some engineering problems there, but they did get a really long way down. It to this day is the deepest hole that we've ever dug as a civilization. So it's pretty cool that they still have that record. And if you ever find yourself in northwest Russia, see if you can make a trip to this place. It's a little bit west of a town of Murmansk, I think, is the town that's nearby. I'm going to show you a map of about where it is in just a second. So this is right off of Google Maps. Here we can see Europe over to the left, right here. This is Europe. Here's North Africa down here. Here's India in here, China over here, China and Mongolia over here, and then of course right up here is Russia. And now Russia's not quite as big as it looks on Google Maps, but um, it gets the job done for the purposes of this of what we're talking about here. So here's Russia, Moscow and St. Petersburg. Moscow's somewhere over here, St. Petersburg somewhere over here, and Murmansk and this Kola super deep borehole are like way up in this little corner of northwest Russia, right next door to Finland. Right here is Finland. This one right here is Finland. So it's right next door to Finland, and pretty close to Norway as well. I think the Norwegian border extends to somewhere up here as well. But basically that little red marker is where the Kola super deep borehole is. So it's a pretty remote location. The crust under that is 35 kilometers thick, which posed a problem for the drilling because they only made it 12 kilometers down. But they could see by the time that they were getting down there, that the planet does start to get a lot hotter. There are a lot of mines in the world that have temperatures of like upwards of 50 degrees Celsius, upwards of 60 degrees Celsius, and it's due to the internal heat of the planet. And that became especially clear at this borehole where the temperature was almost 200 degrees Celsius. Um, Now we're going to start exploring a little bit deeper than that into the mantle and the core. So the mantle starts beyond the crust as you dig deep into the planet. So basically, there's if you've got a little diagram of the planet, here's half the planet. Then we've got the crust as that outer layer, and then within that there's like roughly 30 kilometers down is where the mantle starts, and then way deeper down is where the core starts. So basically the goal of that Kola super deep borehole was to dig from the crust up here to the start of the mantle right here. And so the name of that has this special name. It's called the Mohorovičić discontinuity. It's named after a Croatian. Um, and basically that was what the Soviets were trying to dig down to. That's the name of the thing that separates the crust and the mantle, and that's what they were trying to get to. Now beyond the Mohorovičić discontinuity, or Moho discontinuity for short, because I don't think everybody enjoys pronouncing that name. You can just call it the Moho discontinuity if you wish. Beyond that are 4 layers to the mantle. So in this space here are 4 different layers of the mantle, and they're all hot, but they vary in temperature. The deeper you go, the hotter it gets. The asthenosphere, this second layer, is made of molten rock, and it's the movement of the molten layers of the mantle that cause that cause a whole bunch of different things that we see. Most notably, the way the mantle moves is what causes the fragmented pieces of the crust, the tectonic plates on the surface of the planet, to move around. The way those plates move depends on the way things are moving around in the mantle. Now, when I was in school, we sort of discussed that, okay, the crust is solid, the mantle is this big molten mess. It's basically just lava underground, and then the core is also a little bit molten and a little bit solid. Uh, that's not maybe the best picture, because then it seems like we're basically this big magma drop with a really hard, uh, core and a really, really hard outer shell. But it's not like it's this entirely liquid planet. Basically, deep within the planet, it's still technically a solid, but the way the things around the mantle move, aside from the more molten layers like the asthenosphere, layers that are pretty much solid over really, really, really long periods of time, thousands of years, millions of years, billions of years, they behave like a really, really thick liquid. And I say thick liquid because if you try to pour water out of a bottle and you try to pour honey out of a bottle, there's a difference in how they move, how quickly they move, how much comes out, and things like that. So it's like it's a similar idea to that. It's the property at play with those liquids is called viscosity, but I'm not going to be quizzing you on that. Um, but basically, the idea is that it behaves like a really, really, really thick liquid. So it's effectively solid, but over time, the way it moves is like that of like honey times a gazillion. Like it's like a really, really thick honey, basically. Except it's rock and it's really hot, and in some places it's molten. Um, yeah, so the different layers have different temperatures, and I've written here they have different rigidity. That means that some layers are pretty much their shape is pretty much already decided. For other layers, they're a little bit easier to mold into different shapes. So if you have a new mountain form somewhere on the crust, that mountain is heavy and it can cause the mantle to get a little bit bent out of shape in the layers that aren't so rigid. The layers that behave a little bit more like a plastic than a rock, they'll bend and move due to the weight of the mountain that's above them. So the different layers have different temperatures and different rigidity, and they're made of different stuff. But all together, we combine them into this big thing that we call the mantle. And as discussed a couple of minutes ago, the mantle is responsible for plate tectonics because the movement of hot and cold magma, it's not actually cold, but slightly hotter and slightly colder magma um, from near the core to near the crust and back again will cause the crust itself to move across the surface of Earth. Now, finally, before I get to a couple of pictures, we will talk about the core. So the core is basically the center of the planet, and it's made out of two pieces. There's an outer core and there's an inner core. The inner core is made of solid iron, and it's really solid due to the pressure. Uh, the outer core is molten because the pressure is a little bit less, and there are some like impurities in the outer core. So it's not like pure solid iron like it is in the middle. It's iron and some other stuff in the outer core. Now the outer core moves around a lot and it churns its way around the inner core, and this is what is responsible for creating the planet's magnetic field. It has basically it makes the Earth a giant magnet, and what magnets all have is a magnetic field. So a little bit of physics for you. So if you had a magnet that's like this, so we've got like a north pole here and a south pole over here, let's say, on our magnet like this, then The magnet has these invisible lines called magnetic field lines that basically connect the north and south poles together, and they look something like this. This isn't going to be a perfect drawing because I'm trying to draw this on PowerPoint. But basically, magnetic field lines look something like this, and the planet's magnetic field lines look really similar. So it's this kind of structure that we see in the magnetic field lines, and the details of it are really complicated, electromagnetic stuff. Um, but yeah, so this is what we see in magnets, and it's basically what we see with the Earth, except instead of our north and south poles being like that, they're more like this. So we've basically got our north pole here, our south pole here, but on the size of the entire planet. So the planet is like this. And that big magnet is essentially what we get from the motion of the outer core. That's what creates this magnetic field that we get. So the same magnetic field that I've drawn at the top there is basically what we get at the bottom, is that the Earth has these invisible lines of magnetism, and it's responsible for a whole bunch of different things. We make use of it when we're trying to find our way with a compass. The needle of the compass basically points towards magnetic north, so it basically points towards this N, and that tells us which way we're facing and where to go. But more than that, the magnetic field of the planet is also responsible for protecting us from a whole bunch of stuff that's coming from the sun. The solar wind is basically this stream of charged particles that come from the sun, and if it weren't for a magnetic field to deflect those particles away from the planet and the planet's atmosphere, we would lose our atmosphere and basically all be baked by the sun. On top of that, the northern lights and the same analogous phenomenon in the southern hemisphere, the aurora borealis and aurora australis, are also caused by interactions with the planet's magnetic field. So stuff coming from the sun, and it kind of gets trapped in this area above the North Pole and this area above the South Pole, and that's where we get the northern lights and southern lights, if you will. I'm going to show you guys a couple of pictures before we round this off. But yeah, if you have any questions about these different layers and the things we've talked about, let me know. But also make sure that you watch that video about the Kola Super Deep Borehole. So here's just a picture of the northern lights, or aurora borealis, in Norway, and this all comes from electromagnetic interactions between the stuff that's coming from the sun and the Earth's magnetic field. So we see it really, really far north and really, really far south, close to the north and south magnetic poles. Yeah, I just thought this was a nice picture of the northern lights. So here you go. Now here's basically the diagram I was drawing before. You can see that it's got the same sort of setup. These blue lines on the right are very similar to what I was drawing before, like our big giant magnet with our north up there and our south down here. These blue lines are basically the magnetic field lines of the planet. Now the sun is over here, sending a whole bunch of deadly stuff, charged particles, all these different things are coming our way. And because they're charged particles, when they hit the planet's magnetic field, they get deflected around the planet by the magnetic field. So they come up to the magnetic field, and then as they interact with Earth's magnetic field, they get deflected and go around the planet pretty harmlessly. Now, sometimes those particles and stuff, they'll get trapped in this kind of space around here, in that kind of space there, and in this kind of space over here, and then that's when we see the northern lights kind of here, like a little halo there, and a little one down here in the southern hemisphere. So that's because of the way the magnetic field lines work, that near the North and South Pole, those kinds of phenomena can occur. And last but not least, just because of my spacey kind of background, here is the magnetic field of Jupiter. So this is just without the stuff coming from the sun. All the blue stuff you can see here are the magnetic field lines of Jupiter. Don't worry about the dotted white lines and stuff in this picture. I just wanted to show you a diagram of the magnetic field without focusing on the stuff that's coming from the sun. You can see a little bit of it though. These yellow lines here are the stuff that's coming from the sun, the solar wind, that they are approaching Jupiter, and then as they get close, they get deflected that way and that way. They basically get deflected around the planet. And that's thanks to Jupiter's magnetic field, which is tremendously strong because Jupiter is so big and has so much stuff in it. The one thing I could point out here is that the two dotted lines here and here are different, and the reason for that is the way things move around within Jupiter. This line right here tells you how Jupiter spins on its axis. So if you were to watch Jupiter and its clouds and stuff, it would spin around that axis, but its magnetic field, its north and south pole, follow this one. So basically what we have with Jupiter is that here's the planet, here's the axis that it spins around, but its magnet, its giant north-south magnet, looks like this. So it's not perfectly lined up with the way it spins. So it spins around like perfectly flat like that, around this perfectly vertical axis, but then it's the magnet looks like this, so it's a little bit off center, and then as a result, the magnetic field lines, they don't care about how the planet spins, they care about the orientation of that magnet. So that's what we get over here, is that we can see that these magnetic field lines here, they all converge in line with this white line going like this, which is the magnetic axis of the planet. Now, you don't have to worry about those kinds of words, magnetic axis and rotation axis and stuff. I just thought this was a cool picture and wanted to show you guys a little bit about it. But yeah, that's about it for this lesson. If you guys have any questions, let me know. Otherwise, I will see you all in the next video. Don't forget to do your assignment. Have a good one.